Okay, so we were already introduced by the admins or the hosts here, so I guess we can get started. So our agenda today is as follows. So we'll start with the basic, a bit of a repeat what Felix just said, a basic overview of confidential compute, and explain what are the important characteristics in cloud-like environments for confidential compute. Furthermore, we talk about the different ways trusted execution environments can be used for cloud-like workloads. Cloud native deployments today create very unique challenges for confidential computing, and that is going to be the main topic of our talk today. We'll list some of the challenges that we have identified and propose a few ideas how to tackle those. And to wrap up at the end, we will look at where we are today and what could be the next steps in this area. But first, a quick one-slider about confidential computing. So it all starts with the hardware supporting it and the hardware capability to create so-called trusted execution environments. These trusted execution environments guarantee the code integrity and data confidentiality, but most importantly, they also provide the capability to remotely attest that the TEE runtime is as it's expected to be. Confidential compute is very critical in today's multi-tenant cloud environments, where even your friendly CSP is not considered trusted anymore, not to mention the peer tenants using the same hardware platform simultaneously. As of today, we have several different hardware vendors providing their own solutions to the market. Companies like Intel, AMD are being the most commonly used nowadays. So when we talk about confidential computing, one key element to it is to understand the definition for what is trusted compute base. The trusted compute base and a broad definition is that it is the set of hardware and software components that is critical to your application security. But for confidential or in confidential computing context, we could also think of it as the trust boundary. So what are the potential what are the elements with potential access to your confidential data? Without confidential computing, basically your whole hardware platform can be considered to be part of the trust boundary. So no protection whatsoever to your confidential data. There are also ways to build smaller TEEs using process-based isolation technologies such as Intel SGX. So is Intel SGX here. So with Intel SGX, you can build very small-sized application libraries that process your confidential data, and it's easy to control the TCP size, and it helps to build very small TCP sized applications. But what has become very common in today's environment is the virtual machine isolation techniques, where the guest OS and the virtual machine can be built into a single confidential VM environment where the host operating system, the host platform, and the hypervisor are all considered to be outside the trust boundary. And in our talk today, we are mainly going to focus on this VM isolation. VM isolation challenges. And so next, let's talk a bit about Kubernetes and cloud-native workloads and how these virtual machine level isolation techniques can be leveraged in Kubernetes type of environment. So sort of different flavors of using confidential VMs with Kubernetes. So first we have the fully confidential Kubernetes cluster where each worker node and the control plane are all run in their own dedicated virtual machines. Workloads/pods are being deployed in a fully trusted, fully secure cluster, and in these cases also the control plane can be considered to be trusted. Second, we have confidential virtual machines orchestrated by projects like KubeVirt. In these cases, the cluster runs on bare metal hardware, and these VMs are being orchestrated by Kubernetes essentially. Third, we have the confidential containers that are being run in their own dedicated small-sized confidential VMs using pod sandboxing using Kata containers. In our talk, we basically here we focus on the confidential containers setup that runs on bare metal hardware, Cocoa confidential containers. We also have another flavor that also can run on cloud environments, but that is not something that we are going to cover today. Moving on to the attestation topic, and this is what our talk is mainly about. So, what is included? What is included there? So, the RATS team, the RATS IETF team has worked on this high-level architecture and several detailed specifications for the various roles that are being included in the full attestation flow. Here in this talk, we cannot cover every piece of it, but we mostly focus on the attester piece that runs in a confidential VM environment, providing the evidence to the verifier, and then the verifier then uses some golden reference values to do its verification. For cloud native workloads and cloud native environment, the key promise with containers essentially is that you just build your workload once and run it anywhere. So without necessarily knowing the type of environment it is eventually going to be run in. So we have environments like CSP provided data centers, but we also can deploy the workloads in different types of edge clusters, even in environments where the cluster is composed of heterogeneous hardware architectures. So it is not known whether your workload gets run on hardware vendor X or Y. And then with the one cloud specific promise, or the goal is that your workloads, they come and go, they are scaled up, scaled down, depending on the load demand, or they may end up getting migrated from one node to another due to some node maintenance or some other reasons. And this cloud promise uh, uh, or these type of cases sort of raises unique challenges when we talk about confidential computing, and Malini is going to be talking about those challenges next in more details.
So thank you, Mikko. So let's take a look at the challenges for attestation. Where's all the variation coming from? First and foremost, we'll have multiple vendor hardware. And it doesn't stop there. You have generations of hardware. For instance, with AMD, we already have 3 generations of confidential computing solutions. Intel has already released its Sapphire Rapids, and the next one available right now on the market is Emerald Rapids. If nothing else, the BIOS on these systems across each generation changes. Then you have kernel, you know, 6.1, 6.2, 6.9, and so on and so forth. And then the security patches, the command line parameters, these all introduce variations too. And then we have event logs. There are multitude of these, and they have different formats, different locations. So you have the pre-OS ones, then the OS event log, then you have system D event log, IMA event log, and so on and so forth. So that introduces another layer of variations. If that's not enough, you also have Linux distributions. You know, have multiple vendors like Ubuntu, Canonical, Red Hat, etc. And also we have different Kubernetes distributions, and they have different versions too. And if that's not enough, you also have the actual workload itself. And the whole point of cloud is that you can build often, release often, like a SaaS service. So if you had to keep track of each of these measurements, it's more than a full-time job maybe. And an important part of the cloud is this ability to scale up and down. So you want to be able to automate all this. And why are we alluding to all these variations? Because if you're going to have to check for some golden value, a fingerprint of where something is running and what it is, all these variations can just multiply and give you a combinatorial explosion of values. And that's a lot to handle, and it's a lot to keep updated with. Other considerations are tenant privacy. If you're working in a confidential cluster like Edgeless's Constellation, one of the things that happens is workloads come, workloads go. And if I was to send all the information about different workloads in the cluster to an attestation service, you're leaking information about other people's pods. And if the attestation service, we hope it doesn't become malicious. If it were to be malicious, it would have information about all the vulnerabilities in the workloads that are running on a particular infrastructure or a particular cluster. So that's something to consider when we do attestation. Another important thing is keeping up to date with all these golden values. So if something changes, you have to remember to send it to an attestation service and say, hey, you were looking for 1234 as the golden hash. Now it's 5678 type of thing. And that keeps changing. Next slide, Miko. So, as Miko had mentioned, the promise is build once, run anywhere, and all these challenges that we just mentioned hamper such cloud native promises. So, how can we tame attestation? How can we curb this golden value explosion? One, we could do some use case related invariants, only measure the invariants pretty much. Separate component measures. So you say, hey, here's the BIOS, here's the kernel, and you can use that information to obtain, who should have signed it, what its hash is, to at the attestation service itself compute what that golden value should be, so that the end user, the owner of the workload, it's not their onus to keep supporting and announcing what the right golden value is. I mean, they can take care of a profile, they can take care of a policy, and leave the rest to the attestation services, is the ideal here for us. Another important thing, and this has always been there from, the TCG trusted platform module type of days, is a chain of trust. A is measured, then A is verified, and then A measures B measures C, and so on and so forth. So we shouldn't reinvent the wheel there. We should leverage this chain of trust is our declaration here. And last but not least, to tame this attestation thing, we'd like the attestation service to determine what those golden values are. Next slide, Miko. So let's return to those three use cases that Miko mentioned. He had talked about confidential cluster, confidential VM, and confidential container. So those are our three boxes here. So with confidential cluster, the Kubernetes worker node and the Kubernetes control nodes, they're part of your trusted compute base. So everything that you have from that VM, from right to its BIOS to its kernel and OS, that's like the guest OS at that point because it's a VM, and the Kubernetes, control plane, etcd, any operators, any policies, any webhooks, they're all part of that TCP. So what does this mean for us? The base control plane, the base worker nodes are the invariants in the first use case for confidential cluster. With confidential VM, you might be in a Kubernetes cluster, but what you're using is KubeVirt to launch that confidential VM. And that confidential VM or that image that you have is being provided by the end user. So only that end user VM is in your trusted compute base. So the Kubernetes control plane is out of it, the worker node is out of it. It's just that VM image that the end users brought. And then in the confidential container or confidential pod case, the COCO case on the very right, uh, there is a lightweight VM that's brought in. And in that lightweight VM, what you have is the Kata Coco agent. There is a confidential data hub, and then there's the attestation client. So those are all part of your trusted compute base. And the rest is whatever the pod of the end user that's going to be launched in there. So why do we share this? To tell you what we consider invariance, and that should reduce the scope of all the golden values that you need to measure in there. Next slide, Miko. So the second way to tame all this golden value explosion is to keep your component measures separate. So what traditionally happens, whether you're using TPM or a TE solution like Intel's TDX, is these values that you are going to publish to an event log, they get measured and hashed into some register or the other. So with Intel TDX, we have 4 registers. We call them runtime measurement registers, RTMRs. So once you start appending everything there, it becomes a glob, and you say, is the value 5678 or whatever, and that is pretty opaque. And if you're going to have to pretend one value, then you have to keep determining that value, keep publishing that value. But it's much nicer if you can keep things separate, saying, what should the value of your BIOS version 1.2 should be, or what is Linux kernel 6.9 supposed to be, and so on and so forth. And you can keep those components separate. You can measure their signatures, verify their signature, measure their contents, and so on and so forth. So you can estimate, not estimate, it's a real actual value, what that hash should be. So what else do we want to say about this? We would like to have a data structure called a measurement data structure. It's something that you would serialize and publish to the event log to, so you know it's part of that trusted compute base that you're measuring. You can pass this data structure to an attestation service, so the attestation service could use this data structure and whatever policy that you have in place, and then compute those values and say, yeah, everything is good, bad, ugly, whatever. And then we can also leverage secure software supply chains. And if they're not secure enough, we can, that's an action item for us to improve upon, that ensure that you build these things also in TEEs. So you can then compute those values, and then this all becomes one holistic entity to determine what is the right golden value that you should expect. Next slide, Miko. So now let's get to chain of trust. And in this situation, I'd like to start with what Coco does. It has this lightweight VM, as I mentioned earlier, with its Kata Coco agent, its attestation client, its confidential data hub. So that VM image that you bring in gets measured. And if that's got the right golden value, it says, okay, everything is good. But from that point onwards, we hand off to that Kata Coco agent to pull down the pod image, to then ensure that the pod is signed, all the containers in it are signed, the values that they're expecting are exactly what you get, and so on and so forth. So you can use things like software bill of material, hash, signature, etc., to establish that what you're downloading is exactly what you're getting. Okay. And this also helps support strong identity, what Spiffy Spire wants, and why we all want it. And I'll give you an example. Like, suppose you're doing federated learning, you have a multitude of collaborators, possibly different hospitals, and they all bring in their own data, and they want to collaboratively build a single machine learning model, maybe for some cancer detection, whatever. You want to ensure at that point that each of the collaborators is running the exact same model code. Why? So you don't want one malicious collaborator to do min instead of max or something like that. So everybody's efforts gets wasted at that point, or you know. So that's where strong identity comes in. Next slide, Miko. Yeah,
So
go ahead.
yeah, we are getting towards the close of our presentation. So let's look at where we are with some of the topics that we did discuss. So Malini talked about event logs. So with that area, so let's start with the evidence collection, and then move on to the event log writing. So with more TEEs getting the support upstreamed in the Linux kernel, it was identified that, hey, we can't support this vendor-specific IOCTLs in the upstream kernels anymore. So the Linux community started to talk about, hey, how do we build a vendor-neutral way of for TEEs to produce the attestation reports to the users. And that's how this framework, I guess I could call it the framework, config-fs TSM was born, and this now supports AMD SCV Intel TDX since Linux sub 6.7, if I remember correctly. And this, towards the applications, it's a vendor-neutral way of getting the quotes without having the detailed TEE-specific knowledge how to do that. And building on top of that, what is currently being worked on is a mechanism to be it's a mechanism for user space, for workloads to get their measurements extended on those platforms that support this capability to extend to the runtime measurement registries. So there are patches now ongoing to make that upstream as well. And sort of part related, or part of this conversation, it was identified that, hey, it also all the measurements, all the extensions, they also have to be captured in the event log, so that the event log can later on be verified by the verifier, and make sure that it matches to the quote that was provided by the attester. So we are working in the COCO community to define, like, what is the type of event log structure that we need for the cloud native type of workloads, to make sure that the necessary information from cloud like environments are captured in the event log. And one other thing that is maybe worth highlighting here is that there are a couple of projects that are providing even higher level API abstractions for the confidential VM services to build the evidence for the verifier to to check. So in the COCO community, we have a component called Attestation that provides a very high level get evidence interface that is neutral to the application, so that the application doesn't have to know about what is the underlying DEE that it runs on. The attestation agent is capable of providing the evidence through the simple get evidence in the interface. And a very similar project called CCC API is working towards the similar goals, but the API definition is slightly different, so it goes into more details to like get the individual evidence pieces, like get measurements, get quote, get event log separately. Malini, can you wrap up these two slides?
Okay, so where are we with respect to the solutions in place for usages of confidential compute flavors in the cloud native space? So Constellation exemplifies an invariant. It has a base VM image, it has a chain of trust, and the Constellation bootstrapper measures the Kubernetes. So the invariant is there about what's your VM image at that point. Those measures are going into those RTMR registers, and then, like we mentioned, the bootstrapper measures Kubernetes. So things are taken care of. It's going in the direction we would like it to. Next slide, Miko. Coco that we mentioned multiple times, where Miko is also a maintainer. It exemplifies an invariant base image. It exemplifies use of chain of trust, and it also has the beginnings of an inspectable measurement data structure, and that high level use of an API saying just get evidence that you can pass off to the attestation service. The end user application doesn't need to be even aware of any of this. The attestation service can then open this structure and then look at it and use whatever policies that have been specified and do the right thing. So all the pieces inside Coco, whether it's the confidential data hub or attestation agent, that are on the Coco guest site, can talk to the Coco remote service and get whatever secrets they need access to based on proving their verifiability that they're honest entities. Next slide, Miko. So with that, we want to just summarize what the gaps are and what we would love to work together on. What we all need to work together towards is a standardized event log. There is already a proposal out there, and we're requesting some feedback on it. Capture invariance, define an inspectable measurement data structure, and automate golden value determination. With that, we thank you